Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. So in our earlier video, we discussed a concept called hyperconjugation. In this video, we will be dealing with some questions on the concept of hyperconjugation. So if you're watching this video, then I'm pretty sure you must have watched the earlier video on the concepts of hyperconjugation. If not, I'm just brushing you up with some concepts. So what do you mean by hyperconjugation? Basically, hyperconjugation is the delocalization of lone pair of electrons or pi electrons into the nearby empty orbitals. I'm really very sorry for this. Hyperconjugation is basically the delocalization of sigma electrons into the nearby p empty orbitals. Okay. So what happens? Normally resonance means the conjugation of pi electrons or lone pair of electrons onto the nearby empty orbital. But hyperconjugation here means the delocalization of sigma electrons. That's why it is called as no bond resonance. Okay, hyperconjugation is otherwise called as no bond resonance, and it was given by Baker and Nathan. That's why it's called as Baker-Nathan effect also. Okay, so we had dealt with various factors which led to the stability of compounds. We had seen that how hyperconjugation affects various chemical reactions, the stability of organic intermediates and all we have seen in that video. If not, if you want to have a concept about that, you can watch that video. So without further delay, let's move on to the topic. The first question is, which of the following is most stable? Okay, basically this concept is from stability of alkenes, right? Stability of alkenes. This question is from the concept of stability of alkenes. Now what you have remembered is, if the number of alkyl groups surrounding the double bond is more, then that alkene is more stable. Yes, let me write. The concept you here used is, if the number of alkyl group surrounding double bond more stability of alkene is higher, right? This was the concept involved. If the number of alkyl groups surrounding the double bond is more, then the stability of alkene is higher. So let us see all the 4 examples. In the first case, I have a double bond here. Okay, and here what I need to see is the alpha carbon and alpha hydrogen, basically the alpha hydrogen only. The number of alpha hydrogen should be more. If the number of alpha hydrogen is more, then the stability is higher. So if I consider the first example, I have CH3 and 2 CH3 group attached to the first carbon, then a CH, double bond CH, double bond CH, CH, CH3, CH3. So if I see the alpha carbon, this is the double bond, then this is my alpha carbon and this is my alpha carbon. So here in the first case, I have only one alpha hydrogen here, and with this carbon I have one alpha carbon hydrogen attached. I cannot count this hydrogen because this hydrogen is directly attached to the functional group. But alpha hydrogen means the hydrogen atom attached to the alpha carbon. And what is alpha carbon? Alpha carbon is the carbon just adjacent to the functional group, and here the functional group is our alkene. Okay, so here basically this is our alpha hydrogen, this is the alpha carbon, and this alpha carbon has one alpha hydrogen, this has one alpha hydrogen. So number of alpha hydrogen is directly proportional to the number of hyperconjugative structures. So here number of hyperconjugative structure possible is 2. So I can write here basically it has 2 alpha hydrogens. If I move on to B, then I have here C2H5, C2H5, double bond, C2H5, C2H5. C2H5 is formed by CH2, CH3. Okay, the alpha carbon will be this one, and this has 2 carbons each. So total number of alpha hydrogens are 2 to 4, 5, 6, 7, 8. So here I have 8 alpha hydrogens. Now if I see the third option, I have CH3, CH3, CH3 on all the sides. Okay. So there are 3, 3, 6, 3, 9, 3, 12 alpha hydrogens possible here. 12 alpha hydrogens present here. In the fourth structure, I see CH, 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 and to them carbons are, like number of carbon atoms are attached. So I am not bothered about that because I am directly focusing on my alpha carbons. Okay. So how many alpha carbons? 4. How many alpha hydrogen? To each alpha carbon, there is one alpha hydrogens attached. So number of alpha hydrogen will be 1, 2, 3, 4. So 4 alpha hydrogens. So the answer, which will be the most stable, the stability of alkene is directly proportional to the number of alpha hydrogens. So I see more number of alpha hydrogens in the third case. So the more stable structure will be C. Okay. This is the approach to solve questions like this. If I move on to the second one, hyperconjugation is best described as. Okay. Now this question focuses on the definition of hyperconjugation. Okay. So if I see delocalization of pi electrons into a nearby empty orbital, obviously no. If I see pi electrons, then they come under the category of resonance. But in hyperconjugation, mostly delocalization of sigma electrons are there. So let's move on to the other options. Delocalization of sigma electrons into a nearby empty orbital, probably yes. The second one, the effect of alkyl groups donating a small amount of electron density inductively into a carbocation. Obviously no, there is no inductive effect. Inductively means partial delocalization along the chain in a bonded state only. But here what happens? It is no bond resonance. The bond between the carbon and hydrogen has to break. So this is a condition of no bond resonance. So the word inductively makes this statement wrong. Now if I see the fourth option, the migration of a carbon or hydrogen from one carbocation to another. No, the carbon atoms, we haven't read anything about the migration of carbon atoms, right? The carbon atoms do not migrate. Here also the nucleus or the core structure of the atom remains the same. The carbon atoms do not migrate. So the like stating this carbon atom makes this statement wrong. So from all the three options, which is the most suitable option for me? This, the delocalization of sigma electrons into a nearby empty orbital. Okay. We had seen the example. If I am seeing C double bond, CH, H, somewhat like this, and here also something is there. So what will happen if this one is moving on this will gain a negative charge and this will have an empty p orbital. Then what will happen? This sigma electron will shift onto this orbital, right? Then in the first case this will happen, so that this bond will break. Again in the second case this bond might shift. In the third case this bond might shift. But these hydrogen atoms, these are not removing itself out as protons. These hydrogen atoms are present in the vicinity of that carbon atom. Okay. This was like hyperconjugation. If we move on to the next question, the observed dipole moment of nitromethane is higher than the dipole moment calculated from its structural description. Okay. If I see nitromethane, that is CH3NO2. Basically here what happens? Nitrogen is having a lone pair. It can donate that lone pair to oxygen atom. As a result of which what will happen? Nitrogen will get an empty orbital. To that empty orbital, these 3 alpha hydrogens, they will donate their electron density. There will be hyperconjugation. There will be no bond resonance. As a result of which the polarity or slight polarity will develop between this carbon and nitrogen. And this like hyperconjugation is the reason for additive in dipole moment in the structure of nitromethane. Whatever is observed, whatever is calculated, the observed is actually higher. Okay. This is because of hyperconjugation, resonance, inductive effect, none of this. Obviously not inductive effect, not resonance, we have hyperconjugation. Okay. Next is a very interesting question, and this is a question I have discussed in the video itself. So here I want all of you to pause the video and try answering this question. The next is arrange the following carbon in increasing order of electrophilic substitution. In the first case, I am having a CH3 group on top of benzene. Here I am having carbon CH3, CH3H. Here I am having carbon tertiary butyl group basically. All the 3 CH3 groups are placed on the carbon atom. And the fourth case, what happens? CH3, CHH, 2 hydrogen atoms are present over here. So basically when I was talking of electrophilic substitution, electrophile means electron loving species. So electrophile is represented by a structure of E plus, and E plus will migrate to those carbon atom where there is a negative charge. And how negative charge will occur? See, if I am seeing benzene is having a system of pi electrons in conjugation. Now, if there is any group that donates electron to the ring, then what will happen? This bond will shift like this, resonance will be happening, and there will be development of negative charges on ortho and para position. Okay, so basically I can say electron donating groups create a negative charge on electron donating group, create a negative charge in the ortho para position. Again, with respect to any group present, the direct carbon atom attached are the ortho carbon, the next carbon atoms are meta carbon, and the bottom one here, the last carbon, is the para carbon. So there are 2 ortho, 2 meta, and 1 para. So basically electron donating group will create a negative charge on ortho and para position. Now electron donating effect, here we have what we have basically is CH3 group. CH3 shows a hyperconjugative effect, right? So if hyperconjugate, in order to show hyperconjugative effect, number of alpha carbon should be more. So I will have to compare all the 4 structures and have to see which carbon atom has more number of alpha hydrogens. So if I see the first structure, to benzene ring directly a CH3 group is attached. So this becomes my alpha carbon. Number of alpha hydrogen is here 3 alpha hydrogens. In the second case, I have 2 methyl groups attached here and 1 alpha hydrogen. So here I have 1 alpha hydrogen. In the third case, I have 0 alpha hydrogen because here only CH3 groups are attached. So number of alpha hydrogen here is 0. If I see the fourth case, I am having 2 alpha hydrogens. Okay. So if I am comparing all these structures, then the order will be first 3 alpha hydrogen, then 2 alpha hydrogen, then 1 alpha hydrogen, and then 0. So my order comes out to be 1 greater than 2, 4 greater than 2 greater than 3. So the correct answer is 1 greater than 4 greater than 2 greater than 3. So correct option is A. Okay. So this is the approach how you solve these type of questions. Next question. Hyperconjugation cannot be used to explain the following. Yes, this is another conceptual question. If you are clear about what hyperconjugation is, then you can easily answer this question. So hyperconjugation cannot be used to explain the following. First is stability of carbocation. Obviously, yes, it can be used because carbocation means efficiency of electron, and if there are number of like hydrogen atoms which can donate their sigma bond, then number of hyperconjugative structure will be more, then stability of carbocation will be more. So hyperconjugation directly explains the stability of carbocation. This is not the answer, and here in question you have to say which cannot, okay, cannot be used to explain the following. Next is free radical. Again, free radical is a electron deficient compound. So obviously if there are hydrogen atoms which can donate or they compensate the deficiency, then they will increase the stability. So stability of free radical is also explained by hyperconjugation. Next is electronic structure of arenes. Arenes means a double bonded structure. Okay, arene means alkene type of structure. Alkene case. Arene is basically the ring system. Okay, the aromatic ring system. They come under arenes. So obviously hyperconjugation, in some previous questions only we discussed that hyperconjugation is a key concept in explanation of stability of alkenes itself. So yes, like hyperconjugation can be used here. Next is stability of carbanions. See here, carbanions means carbon with a negative charge, and negative charge signifies excess of electrons. Got it? So excess of electrons can only be like the stability in that case can only be explained by the presence of group which withdraws the negative charge from itself. The electron donating groups, like those groups which increase the negative charge over that carbon atom, they add to destabilization of that structure. So in this case, hyperconjugation is always and always the electron donating factor. So like hyperconjugation can never be used to explain the stability of carbon ions. So my correct option is hyperconjugation cannot be used to answer the stability. Sorry. So there is problem. Stability of carbon ions. Okay, hyperconjugation cannot be used to explain the stability of carbon ions. Next question, the kind of delocalization involving sigma orbital is the definition of hyperconjugation. Inductive effect, no. Electromeric, mesomeric, the correct answer is hyperconjugation effect. Okay. Then we will move on to the next question, and this is a very important question. There is a concept over here. So, which is more stable? What you find here is there is CH3, CH3, CH3 groups attached to the positively charged carbon. In the second case, we have CD3, C plus, CD3, CD3. So, H and D, protium and deuterium are the two isotopes of hydrogen. Okay. Now, here you have to see out of hydrogen and deuterium, which will show greater hyperconjugative effect. Hyperconjugative effect means electron donating effect. Now, if I see protium and deuterium clearly, this is H11, this is H12, this is deuterium, and this is normal hydrogen protium. Now, if I see in both the cases, what happens? The number of electron is remaining same, only the nuclear charge is increasing. Okay, the number of electron is same, but the nuclear charge is increasing, or the nucleus is getting bulkier. Now, bulky nucleus means greater attraction of the electrons towards itself. No, so if I see D, deuterium sounds to be more attracting towards the electron than protium. So, will deuterium ever allow the sigma electron to move on to the empty orbital? It may, but in a it will be allowing it, but with difficulty, right? But protium, being lighter than deuterium, can easily allow its movement of lone pair of electrons. So, if I have to compare which will be more stable, then stability directly accounts for the hyperconjugative effect. So, where the hyperconjugation is more, stability will be higher. So, in this case, CH3 will offer greater hyperconjugative effect than CD3. So, the stability order will be 1 will be greater than 2. So, this is the first option. Okay. So, these were some of the important questions, and in this question we have covered all the concepts related to hyperconjugation. If you are not able to answer this question, you can refer to the video we have already uploaded in our channel on hyperconjugation, and then you can come back to this video to solve the questions. That's all for the video. Thank you so much.